Hey guys, it's Chili here. This video is a companion, a bonus video for 3D Fundamentals 22. It shows how I made the final demo scene. So that was originally recorded for 3D Fundamental 22, but I cut it out for time. Here it is. Enjoy. And you can check out the description. Has a link to the wiki page for tutorial 22 of 3D Fundamentals. It's got all the good stuff on there. Link to the code, link to the original video. If you're watching this video, you got questions about anything I did, because I kind of ran through it pretty quickly. You can always ask on the forum or on the Discord. But with that said, enjoy. Now, we have a camera that can move around in the scene, but it's not a very interesting scene. It doesn't look much like any kind of scene you would see in a game. So I decided for the big finale, we'll create something like an actual scene. Maybe a scene from a game that's from like 1992, but still something resembling a scene. So, first thing I wanted to do was basically just, because I'm going to be using a number of different effects in this scene. So I wanted to factor out some of the common stuff into their own, base shader classes that I could use in multiple effects. So I did the base vertex shader. And that just gives us something to inherit from, and it includes our binding functions and our matrices here. So we got the projection, the world view, and the world view projection. And then in the solid effect, no, that's not it. That's just a bunch of renaming. But here we have a vertex shader. It inherits from base vertex shader, templated on our vertex type. And that makes our code here very simple. All we got to do now is write the output function. And it's the same for our specular Phong effect here. All we got to do now is just write the output function. If freaking Windows, stop doing that. Oh, you make me so angry. Sometimes, you don't know how angry you actually make me. But yeah, here it is. Output function. So that's nice, right? We don't like to repeat ourselves. Keeping it dry, better than keeping it wet, which stands for we enjoy typing. In here, so I changed bind world to just bind world view, because we don't need world and view to actually be separate if you were keeping track there. So we reduced the number of bind functions we need. That's great. It's not that important, right? I also created a base shader for the pixel shader. That's a base Phong shader, and it's it has your binding stuff for binding light stuff and other stuff, and it has the actual shade. It has a shade function that does all of the point light and diffuse calculation in here, and it takes a material color and it takes input interpolants, the attributes, right? And the specular and the diffuse parameters, the attenuation stuff and the specular stuff, I make that templatable configuration. So you create structs that have static constant expression constants in them. And then you can template your base Phong shader on those structs to configure it differently. So by default, it gets these ones here. And then those are used in the calculations for the attenuation and the specular stuff. So that's cool. Cool. And if we go into specular Phong point effect, now we see that a lot of that has all just been replaced by something very simple. Pixel shader inherits from base Phong shader with default parameters. And for the shader, we just call shade with the attributes and the material color, which is stored as a member variable. And that's it. So that's pretty simple. Now, I wanted a shader for the walls and the ceiling, because the walls and the ceiling are very big. I didn't want to do an expensive calculation for all those pixels. I didn't want to do the specular, and I didn't want to do it per pixel. So what I did was I created a per vertex point light effect here with texturing, and that's for the walls. So that's going to be texturing with texture wrapping, not clamping. And let's see here. Added obviously a bunch of textures here. So I changed the base Phong texture a little bit. I made it include vec3. And what else did I change? Oh yeah. So for the material color, it takes a vec3 instead of a vec4. not a big deal. For the specular Fong point scene, which was our pre-existing scene. No, that's just the scene. That's not the effect. So we want the vertex light textured effect. This is the new effect that I added. And the vertex shader on this bad boy, it's going to take input with position, normal, and texture. Texture coordinate for each vertex. It's going to output position, texture coordinate, and a light value, which is just a light color intensity thing, vector. And what we do is we do just a point light calculation here with attenuation, all that stuff. Don't do specular. And we calculate the light, which is just the sum of the diffuse plus the ambient light. And then we output that with the texture as it is, and with the position multiplied by the worldview projection. So that's your vertex shader, does your lighting calculation. Heavy lifting done on the vertex level so that we don't have a ton of calls to this. Not as many as you would get if you were doing it per pixel. And then in the pixel shader, we do our texture lookup. We scale that down to a range between 1 and 0. And then we scale that by the light, and then we saturate that, and then we scale that up to the range of our pixel values, which is 0 to 255. So there is your, pixel shader and vertex shader working together to do some lighting and some texturing. Function to bind texture, obviously. And here's the wrapping using modulus. And and in our scene here, we've got a new pipeline here for the vertex light textured effect. Pipeline here. And down here, we are drawing something. I don't know. What have I got here? This is too small. I can't see. Give me more space. What am I do? This is the wall pipeline. Here is the vertices for ceiling. It's actually a ceiling, not a wall, for your information. And I believe we bind a texture to that in the constructor, maybe? Yeah. Pixel shader, bind texture, images, ceiling. So here I just did a little test. I drew a ceiling. Single ceiling. Now in the final scene here, I've downsized some of the textures. So let's take a look first at what I did for the wall. So specular Fong point effect. Or is this the scene? This is the scene effect. Which one is this? This one is the effect. This one is the scene. So for the scene, did a whole bunch of bullshit here. So I turned everything from values that are just, magic numbers embedded in our code into stuff in here that's nice in one place. I can change all the configurations. So here's, we'll talk about the ripple stuff later. Here's the wall stuff. So we got 3 textures: ceiling, wall, floor. We've got a vector of wall, and we'll get to what wall is for a second, but this has 6 things: the ceiling, the floor, and the 4 walls. And I just called it wall. This gives us the scale of texturing. So basically how much we want the textures to repeat for the ceiling, the floor, and the wall. And this stuff we'll talk about that later. Mouse tracker. Yeah, I just moved some stuff around here. Not a big deal. Here's the size of the scene. So the width of the room in both dimensions of X and Z, and then the height in the Y dimension. And we use all those parameters in the constructor. Show me the constructor. Show me the money. Here. To put the ceiling, 4 walls, and the floor into that vector. And I create a little type here called wall. It's just a simple structure. It holds a pointer to the texture for that wall or ceiling or floor. It holds the model, and it holds a matrix transformation that is its position and orientation in the world. So every wall and ceiling, every surface like that has its own object in that vector. And then when it comes time to draw those bad boys, Where is it? Walls, ceiling, floor. Here it is. We bind, stuff that is common to them all: light position, projection, ambient light, diffuse light. We bind all that stuff, and then for each wall, we bind its position, we bind its texture, and we draw it. And there you go. That's the wall stuff. But I also added another effect. And the other effect I added, well, let me show you. So here's the scene. Here's what it looks like with the ceiling, with the wall, with the floor. If you look here, you see the light. I haven't shown that yet, but I've controlled it with a sine. Its position is controlled with a sine function based on time. So it's moving, which gives us a nice dynamic effect there. And I've created this guy here. This is the ripple effect. It's currently messed up. You might not be able to tell, but I mean, it looks really dark, right? And it's weird. It's weird because I messed up the normals, and we'll get to that in a second. But yeah, I created this ripple effect here. And it's basically just a vertex shader that deforms the Z position. This is the Z position, but it's been transformed from its orientation. But anyways, it does a perturbation of the Z on the mesh of this thing. This is just a plain mesh that has been tessellated so that it has many vertices. And then, so when you change the Z, you can't just change the Z. You also have to change the normals, because I'm using a per pixel shading effect here, point light. So you got to also calculate the normals for this new perturbed wavy surface, and I was messing that up. So we'll get to that in a second. So looking back at the history here for the final scene, the stuff for the ripple effect, well, let's see, we changed the plane first of all, because we wanted to control the texturing of stuff on our planes here that we get, because originally we also wanted to control the dimensions, because originally you set the number of dimensions, you set the size, and it would give you a square plane. But I wanted a plane that was a rectangle, and I wanted to control the number of divisions in the X and the Y. And I want to control, the width and the height to give it a rectangle. So we had to modify a whole bunch of this stuff. I won't go over. It's not that interesting. It's not that hard. It was just annoying, really. And we also, when we get the skinned one, we want to control the scale of the texture on here, because originally it would just stretch the texture to the size of the square rectangle. But what we want to do instead is we want to be able to control how big and how much repetition the texture has over the surface. So that's all that this stuff was. Lots of changes, not that interesting. Not going to waste time going over it. The video will be way too long. Pipeline, I just made this const. This draw function had to be const for some reason. It's not a big deal. So that stuff is not really very interesting. But the ripple effect, ripple, vertex, specular, Phong effect. So here, what we're doing is for our vertex shader, we're storing time. We can bind that. There's a function to bind time. Yeah, set time. We're storing some constants. The amplitude of the ripple. The frequency, I named these stupid. Frequency is actually the amount of waves on the surface. And the wavelength is actually the speed at which the animation moves. This should be switched up. And these aren't actually frequency and wavelength if you look at the functions here. But they control, if you understand how sine waves work and how repeating functions work, frequency and wavelengths are just two sides of the same coin, right? But anyways, it doesn't matter. This video isn't about this effect here. I'm just going to give you a quick overview. I don't want the video to be 3 hours long. But the idea is we use cos to derive the Z perturbation. So we get the cosine, that's a function of the X position of the vertex, and it's also a function of the time. This gives you the animation. This gives you the waviness, the static waviness. This gives you the animation of that. And then we multiply that by the amplitude to get the delta X, the perturbation, and we get our position is just positions plus this delta Z, not delta X, delta Z. Now we have to also get the normal. The calculation of normal is very complex. I'm not going to go into it here, but it's basically, for those of you who know about multivariate calculus, it is the partial derivative in the x and the y direction, and then you take the cross product of those two vectors, and you get the normal. And that's what this is supposed to be, but I fucked it up. And you can see that if you look at the actual animation. If you remember, it was all dark and stuff, and that's no good. So I stared my code down for a while, and I said, I don't know. I don't see what the problem is. I'm not even sure if the effect just doesn't look that good, or if I messed something up. So I suspected my normals were wrong. You know, it's been many years since I did multivariate calculus. I might have screwed something up. So what I did was I created a system that would allow me to visualize the normals. This was a big pain in the ass, but it led to a very cool looking effect. So we got visualize the normies, and what I did was I created a new pipeline called the normie pipe, and it adds extra stuff in here in order to draw the normals. So in the step where we process the vertices, after we process them, we then run through all the vertices again, and we get two vertices out of these. So for each vertex, we make two copies of it, V0 and V1. V1 is the same type as V0. That's the decal type thing. So V0 is just going to be the vertex that we're processing. V1 is going to be that vertex, but its position is taken as the nend of that vertex. What is the nend? Well, the nend is the normal. If you imagine our mesh, it's got normals, right? They should be looking something like this. So it has the vertices on the mesh have a position. They have a normal vector, and nend is just the vertex, which is the position, plus the normal vector times some amount. So if you take these 2 points, they will be little line segments that represent the direction of the normal. So that's all this is. You take the vertex position and the nend, and that will give you a line that represents the normal. We make sure that none of these are really close to or behind our viewing position, because if they are, then when we do this transformation, it's going to be a divide by 0, and it's going to mess us up. So we just do some very basic clipping to make sure we don't get screwed up. And we transform these two vertices, the positions, and then we draw a line between them. But we have to draw the line in consideration of our depth buffer, because we don't want to overdraw things or get overdrawn by things. So I had to create a line drawing function that also has depth occlusion. So that's what I did in graphics.cpp maybe? No, I deleted drawline from graphics.cpp. I made a templated drawline. I originally made it templated, and then I untemplated it, but I left it in this H file. So don't worry about it. So draw line depth takes a reference to Z buffer, takes two vertices in 3D space, takes a color. It's going to draw a line between them. It's going to interpolate using interpolation, so we can interpolate the Z, and we use that Z to test and set, so we're drawing correct to our Z buffer. So it's just a line drawing routine, but with Z buffering. Now we're trying to debug our ripple effect here. So to do that, we have to add the nend parameter, the attribute, to our vertices. So we add the nend, and then here we calculate the nend, which is just position plus our normal times a very small amount, because we don't want a super long indicator. So 0.2 does the job. And then in our scene here, we add the normie pipe. And for our pipeline that we use for our ripple effect, instead of using pipeline, we use normie pipe. And that's the only change here. And if we run that, we're going to see something very interesting. We're going to see, okay, this is why our texture is very dark. Our normals are pointing in the wrong direction. You can see it here, right? They are not pointing in the correct direction. This is bad. This is very bad. So when we do the cross product, if we get the cross product parameters backwards, the vector will point in the wrong direction. So first step here is to point the cross product in the right direction. But if you look at these guys, it's not just the direction that's messed up. They're also pointing in the wrong direction. Like, it's not just that they're pointing in the opposite direction. They're pointing in the opposite direction, but also the wrong direction. They're swaying They're walking with a swagger. We don't want them to walk with a swagger.
Yes. I walk with the swagger, right? I walk with the swagger. You know what I mean? I walk with the swagger. Check it out. I walk with the swagger. You know what I mean? Say what?
They got that stanky leg and we don't like it. So, what's the problem? Well, to make a long story short, we fixed some stuff. So in the normie pipe here, I just changed the clipping here a little bit, and I changed the color to cyan because that pops better on the texture that we have. And here's how I fixie. First of all, well, the fix for pointing in the opposite direction is simple. This should be a negative. If you do the cross product in the opposite order, these terms are the same, but they become negative. But there was another problem here, and that is, now the reason why we got that stanky leg is we're calculating the cos here for the perturbation, for the delta z, and that's fine, that's perfectly great. To calculate the normal, like I said, we use the derivative. What's the derivative of cos? Well, if you know basic calculus, derivative of cos is negative sine. What are we using here? We're using cos. So I typed a cos when I should have typed a sine. So the second fix is calculate the sine. So we calculate the angle separately, and then we calculate the cos and the sine of that angle. We use the cos to do the perturbation of z. We use the sine to calculate the normal. So let's take a look at what those normals look like once they've been fixed. And doesn't that look a lot more like what you would expect? Doesn't that look pretty? And you also see that now the lighting on this surface makes a lot more sense. Beautiful. Okay, so final thing we do is, of course, we remove that, even though the visualization actually looks cooler than the normal scene by itself, we remove this debug visualization by setting the scene back to pipeline. And we remove the stuff about the NEND, no more NEND because we don't need it anymore. And here is what the scene looks like at the end. So we got the lighting here. We can also see the specular highlights. You can notice them on the ridges here, on the troughs and the crests. So yeah, shiny, ripply, sexy. The butthole of Sauron, rotating Suzanne, and scene with stuff. There you go. Moving around with a camera. That's it. That's all she wrote.